Imagine a world where machines can think like us. They learn from their experiences. They recognize patterns. They even make decisions. This isn't science fiction. This is the incredible potential of artificial intelligence, or AI. At the heart of this revolution lie neural networks, intricate systems designed to mimic the human brain. Our journey into the world of AI begins with two pioneers, John Hopfield and Geoffrey Hinton. These brilliant minds dared to explore the uncharted territories of artificial neural networks. Their groundbreaking work laid the foundation for the AI-powered world we live in today. Like explorers charting new lands, Hopfield and Hinton ventured into the unknown. They faced skepticism. They encountered obstacles, but their unwavering belief in the power of neural networks fueled their pursuit. Their discoveries ignited a revolution that continues to shape our world in profound ways. We stand at the cusp of a new era, an era where machines learn, adapt, and evolve. This is the legacy of Hopfield and Hinton, the pioneers who dared to dream of thinking machines. Before we delve into the intricacies of artificial neural networks, let's take a moment to appreciate the marvel that inspired them, the human brain. This 3-pound organ, a labyrinth of billions of neurons interconnected in a vast network, is the seat of our thoughts, emotions, and memories. Each neuron, a tiny electrical powerhouse, communicates with others through a complex dance of chemical signals. These signals, traveling across synapses, the tiny gaps between neurons, form the basis of our thoughts, actions, and perceptions. The brain's ability to process information, learn from experiences, and adapt to new situations is a testament to the power of this intricate neural network. Imagine the brain as a vast cosmic web, with billions of stars, the neurons, interconnected by threads of light, the synapses. Each spark of light represents a signal, carrying information from one neuron to another. This mesmerizing dance of signals gives rise to our consciousness, our creativity, and our very humanity. Inspired by this biological marvel, scientists and engineers have long sought to create artificial systems that mimic the brain's extraordinary capabilities. This quest led to the birth of artificial neural networks, mathematical models designed to emulate the structure and function of their biological counterparts. Enter John Hopfield, a physicist with a passion for understanding the brain. In the early 1980s, Hopfield introduced a groundbreaking model for artificial neural networks that would forever change the landscape of AI. His creation, now known as the Hopfield Network, provided a simple yet elegant framework for understanding how networks of artificial neurons could store and retrieve information. Hopfield's network, like the human brain, consists of interconnected neurons. However, unlike the brain's complex web of connections, the Hopfield network employs a more structured approach. Each neuron in this network is connected to every other neuron, creating a feedback loop that allows the network to learn and remember patterns. Imagine a group of fireflies blinking in sync. Each firefly represents a neuron, and its blinking pattern represents its state. The fireflies influence each other's blinking, creating a mesmerizing display of synchronized light. This is akin to how neurons in a Hopfield network interact, influencing each other's states to store and recall information. Hopfield's work was a watershed moment in the history of AI. His network, though simple, demonstrated the potential of artificial neural networks to perform complex tasks such as pattern recognition and memory recall. This groundbreaking work paved the way for the development of more sophisticated neural network models, bringing us closer to the dream of truly intelligent machines. Section 4. The Hopfield Network, a Symphony of Patterns. The beauty of the Hopfield network lies in its ability to store and retrieve patterns. Imagine presenting the network with a picture of a cat. The network's neurons, initially in a random state, adjust their connections based on the input pattern. This process is akin to tuning a musical instrument, with each connection representing a string that needs to be adjusted to produce the desired sound. Once the network has learned the pattern, it can recognize the cat, even if the image is noisy or incomplete. This is because the network stores the essence of the cat, not just a pixel-by-pixel representation. It's like recognizing a familiar melody, even if some notes are missing or played out of tune. Think of a jigsaw puzzle. Each piece represents a neuron, and the connections between them represent the puzzle's interlocking tabs and blanks. The complete picture represents the stored pattern. Even if some pieces are missing, the remaining pieces and their connections provide enough information to infer the missing parts and recognize the original image. The Hopfield network's ability to store and retrieve patterns has profound implications. It demonstrates that even simple artificial neural networks can exhibit a form of memory, a fundamental building block of intelligence. This breakthrough opened new avenues of research and inspired a generation of scientists to explore the vast potential of artificial neural networks. Section 5. Geoffrey Hinton, architect of the Boltzmann Machine. While John Hopfield illuminated the path towards artificial neural networks, it was Geoffrey Hinton who would take the next giant leap. Hinton, a British-Canadian cognitive psychologist and computer scientist, is widely regarded as the godfather of AI for his pioneering work in deep learning, a powerful type of AI that involves training artificial neural networks with multiple layers. In the mid-1980s, Hinton, along with his colleagues, developed the Boltzmann Machine, a revolutionary type of neural network that introduced a new paradigm in machine learning. Unlike the Hopfield network, which relied on deterministic connections, the Boltzmann machine embraced randomness, using a probabilistic approach to learn and represent data. Imagine a snow globe. Each snowflake represents a neuron, and its position within the globe represents its state. As the globe is shaken, the snowflakes settle into a new configuration, representing a different state of the network. This random exploration of states allows the Boltzmann machine to learn complex patterns and relationships in data. The Boltzmann machine, named after the Austrian physicist Ludwig Boltzmann, utilizes a concept called energy to guide its learning process. The network seeks to minimize its energy, much like a ball rolling down a hill, by adjusting its connections based on the input data. This process allows the network to learn the underlying probability distribution of the data, enabling it to generate new data that resembles the training data. Hinton's work on the Boltzmann machine marked a significant departure from previous neural network models. By embracing randomness and probabilistic learning, he opened up a new realm of possibilities for AI, paving the way for the development of more sophisticated and powerful neural networks. Section 6. The Boltzmann Machine. Learning from chaos. Initially, the Boltzmann machine faced a significant challenge. It was computationally expensive and time-consuming to train. This was due to the random nature of its learning process. It was like trying to find a specific grain of sand on a vast beach by randomly picking up and examining each grain. However, Hinton and his colleagues were not deterred. They developed a modified version of the Boltzmann machine called the restricted Boltzmann machine, or RBM. The RBM, by imposing restrictions on the network's connections, simplified the learning process, making it significantly faster and more efficient. Think of a maze. The original Boltzmann machine was like exploring every possible path in the maze, even the dead ends, to find the exit. The RBM, on the other hand, was like strategically blocking off certain paths, eliminating the dead ends and allowing the network to focus on more promising routes, making the learning process much faster. This breakthrough paved the way for the resurgence of neural networks in the 21st century. The RBM, with its improved efficiency, became a crucial building block for deep learning models. Its ability to learn complex patterns and representations from data made it an ideal candidate for a wide range of applications, from image recognition to natural language processing. The Boltzmann machine, though initially plagued by computational challenges, ultimately proved to be a pivotal innovation in the field of AI. It demonstrated the power of probabilistic learning and laid the foundation for the development of deep learning, the driving force behind the current AI revolution.